Hi, in this video I'm gonna show how to use reinforcement learning to get the parameters of a PI controller, a proportional integrative controller, which is a classic controller type. And the example is gonna compare the performance of that PI controller with the parameters obtained from reinforcement learning against the parameters obtained from the control system tuner. And as the article mentioned, for simple examples, the control system tuner can perform well, but for highly nonlinear systems or adaptive controller cases, the reinforcement learning can suit better. An advantage of this example is that, for example, let's say that you have a control system based on classical controllers like this PI controller. You want to generate code for it. Then you can use reinforcement learning to get the parameters, and you still generate code for the classical controller, but the parameters were obtained from reinforcement learning. That's something that this example is going to show. So let's go to the example. First, we have to load the model. And the reward that we're going to use is this one over here, which is basically we're going to use for the environment, which is water tank level control. So we have a desired height of the water tank, and then we're going to fill that tank. So the reward formula for that is going to be, as you can expect, the difference in height, and also we're going to add a penalty for the amount of flow. If you flow a lot of water into a tank, that's not good. The less you flow, the better. So we can see the physics of the water tank controllers are very simple. You have a flow of water, and then the flow of water gets integrated, and you got the water tank height in here. So the height is going to affect the flow of water, as you can see, and the initial condition is going to be 1, and the expected height is going to be 10, the desired height for this very simple example. So the current height is going to be differentiated with the desired level to get the error, and that error is going to be fed into the calculation of the cost, the reward. And also we're going to feed the flow of water from the PI controller for the reward, and we're going to add some noise to the flow of water. Okay, so the reward, as you saw in the formula, is the error. We have a rate transition block to go from one rate to the other. That's a Simulink specific stuff to go through between two different sample times. And basically you have a penalty for the difference between desired height and actual height, which is in the error, as I mentioned before. And the penalty, you have the penalty here for the flow of water. So as you can see, there's no positive reward, so you're going to expect a negative reward that we want to minimize. Okay, so now that we have them all, now we're going to establish the sample time, which is going to be 0.1, and the final execution time of the model, which is 10 seconds. Okay, so now we're going to use the control system tuner to get the optimal parameters for that particular water tank. Right now, okay, yeah, now the model updates because we have the sample time. That was the missing thing here, but we opened the control system tuner, and the control system tuner has can optimize various types of controllers. And in this case, we are going through a proportional integrative, which falls into a general category of proportional integrative derivative, PID. And you can see the constant for the proportional, the integrative in here. This is actually, yeah, you can see that we have PI, no PID. So that's why you see only those two terms. And the integrative right now is 1 to the -6. Okay, so, and then the tuning goal is going to be the linear quadratic Gaussian. That's the goal, and we have to put the noise signal. And if you look at the model, you're gonna see them in here. This is the noise signal, and this is the PID signals, the output, the U, and the error. So you have to specify those, and then some parameters for the LQG objective, and then going back to the controller. Although this is not the scope of this video is reinforcement learning, but just to show briefly how this works, then just tune it, and we're gonna get the PI parameters from it, which in this case are gonna be in the mole, which is 9.8 and 1 to the negative 6. Okay, so if you simulate this, you should be able to see the water level. You can see that it is not it's not exact. It gets to the top pretty fast, but it doesn't get close to the water level, desired water level, which is 10. So we're gonna see how reinforcement learning improves that. So let's close this, and let's close also the control system tuner. For future reference, we're gonna keep those variables, those values in these variables, and now we're gonna create the reinforcement, the environment. We have for the reinforcement learning. We're gonna do the same. We're gonna get the PI parameters from the reinforcement learning. So for that, we have this Simulink model that is gonna be very similar. We have this in red because we haven't created the agent yet. So the reward is gonna be the same. The error, the height error, and also the flow, the flow usage are gonna be a reward. We're not gonna have a terminating condition, although for this example we could have one. If you're overflow, then terminate, but we don't. The example choose not to have it. And the observations are gonna be the water level error and the discrete integrative of that error. So we have two elements in the observation vector, and the action is using the reward is going to be the previous action. That's why we have a unit delay, and the physics of the system are exactly the same as well. The desired water level is going to be 10. So let's create the agent, and first create the environment, and we have this function from the example. And in here we have to specify always the interface. The interface between the agent and the environment is going to be the observation, and in this case we have two elements for the observation, both of them contiguous, and we have the action, which is scalar, that is the flow of water, which is going to be contiguous as well, numerical spec. Both of them are numerical spec, and then given the observation, the action, and pointing to the block. The name of the block is RL agent. Within the model, so we specify the path to the block, which is this one, and the model and the observation and the action, and we have the environment based on Simulink. We have to create this a reinforcement learning toolbox. Depends on MATLAB classes, so we have to create a MATLAB class. Even though we are using a Simulink model, this MATLAB class has to point to a Simulink model, and that's what we're doing here. We have to create a reset function that is going to reset the parameters in the Simulink model. In the case of the desired water level, we're going to randomize around 10, slightly around 10, and the initial height is going to be 0. And the parameters, you can see that you have the path. This is the path to both blocks, the desired water level and water tank age. And you can see that desired water level, this is one of the parameters, it's just a constant, and this water tank system age is going to be the initial condition for that integral block. So those are the parameters that you're resetting in that function, and you provide that function as a lambda, passing the model and this input. And now with that, we have our MATLAB reinforcement learning environment for that particular model. So we're gonna get the number of observations, which is 2, the product of the sizes of the dimensions, and the product of the sizes of the action, which is scalar, so you just have only one element. So that's gonna be used for creating our networks. We're gonna use range 0 to the seed of randomization is gonna be 0 for reproducibility of this example. And now we're going to create the actor network, but before creating the TD3 agent, I'm going to give some brief background about that agent. So this is the Twin-Delayed Deep Deterministic Polycity Gradient agent. Is an agent based on DDPG. It's like an improvement on DDPG, and one of the main features is that it's going to have a couple of critics, and both the actor space is contiguous, and also the observation space is contiguous. So let's take a quick look. It's gonna perturb the actions chosen by the policy using a stochastic noise model. So this is for exploration, I understand. When you perturb the action randomly, is for doing some additional exploration during training. So we're gonna use a parameter for this in our example. So for our perspective, let's take a look at where the TD3 agent is. It's gonna be an off policy, so it's gonna be trained without the policy, and it's gonna have an actor critic. The action space is contiguous, and it's like policy gradient. So like a deep deterministic policy gradient, both of them are going to use the same functions to create the actor and critic. So in the case of the critic, it's RLQ value function, and in the case of the actor, it's going to be RL continuous deterministic actor, because the actor is continuous and also deterministic. And as you can see in here, the TD3 is a little more complex than DDPG, and as you can expect, it can perform better, but it's going to take more training time. But in this simple case of water height control, it's gonna be quick. It takes 11 minutes for the article, as the article mentions, but it took me like 30 minutes. It's very quick. Okay, so in terms of the training, it's gonna have a queue for the expected long-term reward. But since we have two critics, we're gonna have two of them, and that's expressed with the k in here. The k can be 1 and 2. That's why you call it twin. And the phi is the learnable parameters. This is the observation state and the actions. And for each critic, you're gonna have a target. And also for the policy is gonna be a pi, and the pi has the theta parameters, and you're gonna have a target for the actor as well. And for training the critic, you're gonna compare as usual the expected reward versus the actual reward, and the actual reward is gonna use the target, and the target is not updated as frequently as the corresponding critic. So these networks, the target for each agent can have different architecture, neural network architectures, but the corresponding target for that particular critic has to be the same architecture, but the parameters, as you can see, are different. You can see this phi target k. You can see it can be phi target 1, phi target 2. Those parameters are going to be different, and they are going to be updated based on this. So these are updated less frequently, as mentioned, and they're going to be used to compute the long-term reward. There's a decay constant that is specified in the agent configuration. And notice that to get the expected reward from the target, you're going to use the target policy. And that uses its own parameters as well, that are updated in the similar fashion. So this is added to the accumulated reward in the episode, and that's your actual, supposedly actual. You can not get the actual long-term reward. You can estimate it, like we're doing here, and that is subtracted with the predicted long-term reward, and just average over the m, which is basically the. I understand that it should be the batch size. Of your sample. The batch size I think is 128 usually, and the sample buffer where you collect the samples is much larger, like 1 million or something like that. Okay, anyway, that's for training the critic, and for training the actor. In the actor, you don't want to minimize the error like in here. You want to maximize the reward, and that's why you use the gradients. The gradients put the differential direction in the direction where it maximizes the reward. And in here again, you're using the predicted reward and the non-target policy, and then compute the gradients based on that. And at a given configuration time, you update the targets using the regular parameters, and as the other models that we have seen, the smooth factor determines how much of each one of the target and non-target you get, and you configure the frequency at which they are updated. Okay, So that's the TD3. Now let's go to example to create it. First, we have to create the actor, which is a very simple network. It takes the observations as input, and the output is going to be just the water flow. And we specify initial gain, which is just the initial weights for the network, just to have a starting point for this example. I guess that helps to get the PI controller weights at the end. So, and let's take a look at the network for this actor. Whoops. Actually, it was the actor, not the critic. So we can see that the input is the observations, and the output is gonna be, it's very simple. It's gonna be the flow, and this is by design that this is very simple. And the reason is that if you notice, the PI controller is a block that has two parameters, the proportional gain and the integrative gain. So these weights in this network are going to simulate the PI controller. That's what it's doing. The example doesn't mention it explicitly, but this is simulating the PI controller, this very simple actor. Okay, now that we have the network and we have the observations and the actions, then we are going to create the actor, one down. And now we're going to create this with this local function. We're going to create the critic, which is similar to what we have seen in other examples. We have the branch of the observation, the branch of the action, and then we concatenate them and have a ReLU with 32 units of the filter, and eventually we have a scalar, which is the long-term expected reward. I'm just gonna run it and take a look at it. It's not different from other examples that we have seen, that we have the observations with two elements, the actions, the fully connected layers for each branch is 32, so that they can be concatenated, but they're concatenated in one dimension. So now we have 64, and then we just turn it to 32 and eventually to 1, which is the long-term reward. Okay, so now we are going to create a twin delay. That's a feature of one of the features of the TD3. We're going to create two critics. And in this case, they have the same architecture, but they could be different architectures. And we have to specify the input for the observation and action for those two networks when we create the critics. Yeah, so we have to specify observation, action, and network, and the inputs of the network. That's it. So we have the critics. We're going to put them into an array, and now we have to specify the options for the actor and critic for the training, which is the learning rate and the gradient threshold to avoid the gradient explosion. And they're going to be the same this time, the learning rate for the critic and actor. And then the TD3 options is going to be the sample time, the mini batch size 128, the experience buffer where we create the samples for training, and the options for the actor and the critic. So we have all the TD3 options. And finally, this is the target policy smooth model, a standard deviation. This is for the noise for exploration. That's my understanding of that. And so we now have the options. We have the actor, we have the both critics in an array, and the actor and the agent TD3 agent options that we just created. And now we have our agent, and if you go back to the model, now it should not be red. It should be, yeah, because we created our agent. Okay, now the training options is basically the maximum steps, final time divided through sample time, 10 divided by 0.1, which is 100 steps. And we're gonna have maximum episodes 1000, but it should converge way earlier than that. And basically we're gonna know the verbose, put a display, and the average reward is we're gonna stop when the average reward is negative 355, as I mentioned before. We're expecting a negative reward because we don't have positive rewards. Everything is negative. And so now with this, we're gonna train it, and as you can see, it starts bad as always and eventually gets to negative 355, and it took 11 minutes, 370 episodes out of the 1000, so it converged pretty early. And I'm not gonna run it completely because yeah, it takes about 11 minutes, but you can see that it's running there. I'm just gonna stop it. Okay, I'm gonna close this, and now I'm just gonna load the agent, the train agent, to proceed with it. And I'm just gonna make sure that the agent is working fine by simulating. Whoops. Okay, I relaunched MATLAB. What happened there was that if you have the train method, run the tool to train the reinforcement learning agent, and you stop it suddenly, it's gonna have some problems in there. It can take a lot of memory, and you might have to end up restarting, but it's better to let it finish. But if you stop it early, it kind of messes up the system and you might need to restart it. So okay, so anyway, I'm gonna simulate the model. I already run all the steps again and loaded the train agent already, and I'm gonna just run the simulation just to, and I'm gonna take the rewards. I'm gonna see the rewards in here. We're gonna see both filling the water tank. Let's first fill the water tank and see how it looks. So this is the scope. So I'm gonna make sure that the initial height is low, or the water tank isn't 0, and we want it to be the desired water level is gonna be 10 point something. Okay, let's run it, and we're gonna see that it starts low and it jumps a little bit high and eventually gets to the desired water level pretty accurate. Okay, so now I'm gonna take a look at the experiences, the reward in particular, and we have the data in here. So let's just plot it to take a look. So as you can expect, the reward is gonna be very similar to filling the water tank. It's gonna start very bad, and then the reward is gonna be 0, because yeah, you don't have to apply water flow and you're very close to the water level. So but still, while you get there, you have to you're gonna get some negative reward, so it's impossible to have 0 reward in this particular case. Okay, so now let's compare what we get from the classical optimization versus reinforcement learning for getting these PI parameters. So for that, but first we're gonna put the weights of the neural network into a PI controller, and for that we use a actor equal to agent. From the agent we're gonna get the actor. That is a method from the agent class, and from the actor class there's a method to get the learnables, and from that you can see the learnables, which as we saw are 2 elements in the weights, 0.4 and 8, and those we're gonna use for the PI controller, and we're gonna put them into, both of them are positive, so we don't have to use absolute value. But anyway, we have the key the parameter for the integrity part and the proportional part, and we're gonna put those in the original model. For the PI controller we're gonna use the path to the blocks, and those are the parameters, the P and the I parameter, and we're gonna put those 2 values that we just had in here, and we're gonna see it in a moment. You can see it in here. Okay, so you can see in the P controller that we have PID controller that we have 8 and 0.4. Those are the values that we obtained from the reinforcement learning. Okay, so now let's take a look at filling it, but first make sure that the initial value of the tank is low, is 1. So we're gonna go from 1 to 10. So let's see, Control T to simulate to see how it was, and you can see that it performed well. It went to the level 10. It jumped a little bit, but eventually get close to 10. So the control behave fine. And now let's compare it to the classical optimization. So first, I'm not gonna use this function. I'm just gonna use the output of the water level, which is this RL step. I'm gonna put the output, the actual water level, into the RL step variable. And then I'm gonna put, if you remember, we saved the classical optimization parameters, which were 9.8 and 1 to the negative 6. We placed them on this variable, so we're gonna put them again in the model and simulate again. And you can see that we have 9.8 and 1 to the negative 6. And let's take a look at the simulation output, and you can see it's not that good. I mean, it converges quickly, but it doesn't get really never into the desired value, so that's a problem with that. Okay, now let's compare with a plot, one to the side of the other. In simulation output, we're gonna save it in the classical optimization variable, and then let's just plot it. Okay, so we can see here the reinforcement learning is in red and the control system tuner is in blue. And you can see that the classical one did not get close to the desired water level, while the other one really gets closer to it. But the classical optimizer is gonna converge quicker than the reinforcement learning one. Okay, so in summary, in this example, we saw how to use reinforcement learning to get the parameters of a classical control system controller, like the proportional integrative derivative. And with this, you can know that, and this is the reinforcement learning approach is something that is convenient for control cases where you have a bunch of high nonlinearity and also adaptive cases. And it's easy to get these parameters, put them into your controller, and deploy them in your embedded system with code generation, with C++ code generation. Okay, and also you can see that even for small problems, the reinforcement learning could be effective. Okay, that's all for the video. Thank you very much for watching.